Hello everyone, this is part 3 of our review for exam 1, going over selected problems from our review sheet. And last time we left off with the concept of fitting the form for e to the u, where we have a product of algebraic factors and exponential factors, and remember the exponentials dominate. So in letter I we had a situation where our choice of u was the exponent on the base of e being a polynomial, and it fit the form neatly. And then in letter P, we had a situation where it was a little bit more complicated, but again the exponentials dominate over the algebraics, so our choice of u was again trying to fit the form of e to the u by choosing u to be the power on the base of e or the square root of x. And we just had to be a little bit more careful in terms of calculating our du, but we were able to show that it fit that basic formula for the integral of e to the u. So, once again, if we have a product of algebraics and exponentials, exponentials dominate. But now we see in letters J and R that we have a product of exponentials and trigs. And when we have this situation, we don't know which one dominates. It could be the exponential, it could be the trig. So you just have to think a little bit. Now if we look at letter J, what are the choices? Well, I see an e, and so the integral of e to the u with respect to u is a choice. And then we see the sine function. So the integral of sine of u with respect to u is a choice. And it's usually pretty easy to discern which one we're going to need to use because, for example, you just have to think a little bit and run through the scenario. If we were to choose to go for sine of u, that would mean our u would have to be 5x. Now we know our du needs to be satisfied, and good luck generating all the rest of this to represent the du. So it's pretty easy to discern here that e to the u is more than likely going to be the correct choice. So we're going to choose our u then to be the cosine of 5x, and once again that is in an attempt to fit the form for e to the u with respect to u. We have to calculate our differential du. Make sure you put yourself in the differentiation mode. The derivative of cosine is minus sine. Same argument, 5x. Don't forget times 5, the derivative of the argument, and the differential dx as well. And then we're going to modify by the negative and the 5, so we have that negative 1/5 du equals sine of 5x times the differential dx. Now, when we look back at the integral, we know we've already established e to the u. The leftover factors are sine of 5x dx, and we compare them to our du, and we see that they match, just modified by the negative 1/5. And so therefore, we've accounted for all the factors of the integrand. We're ready to make the change of variables. We'll bring out the negative 1/5, and upon the change of variables, we get the basic formula for the integral of e to the u. And so that integrates to be e to the u, so the negative 1/5 tags along, times e to the u, add our constant at that point, and then back substitute. So minus 1/5 e to the u was cosine of 5x, and then plus our constant. Okay, so then in letter R, we see a similar situation with respect to the fact that we have an exponential and a trig. So here, the choices again would be either e to the u with respect to u, or in this case, the integral of secant squared of u with respect to u. And once again, it's usually pretty easy to discern which one is the correct one to shoot for, because, for example, if we're going to try to fit e to the u, we'd have to focus on this factor of e and choose our u to be the power, 3x, and knowing the du needs to be satisfied, obviously the derivative of 3x is not secant squared of whatever. And so therefore looks like we're going to have to try to fit the form for secant squared of u by choosing our u to be 1 minus e to the 3x. Now, I argued those mentally. If you have to write something down, that's fine as well. But again, with this problem, we're trying to fit the form for secant squared of u. So there's our u, our differential du. Again, put yourself in the differentiation mode. The derivative of 1 is 0. The negative tags along, derivative of e to the 3x. That's our formula for e to the u, so it's e to the u. Just recopy e to the 3x, but then don't forget times the derivative of the power on the base of e, and the derivative of 3x is 3. Formally, the differential dx as well. And we'll modify by the negative and the 3, so negative 1/3 du is e to the 3x times the differential dx. And if we look back at the integral, the leftover factors are the e to the 3x, differential dx. Compare them to our du, and once again, no surprise, they match. In this case, just modified by negative 1/3. So all the factors of the integrand are accounted for. We're ready for the change of variables. We'll bring out the negative 1/3, and upon the change of variables, we now have the formula for the integral of secant squared of u with respect to u. And so you should know that secant squared integrates to be tangent, because the derivative of tangent is secant squared. Look amongst the formulas if you need to. So we get negative 1/3 tangent of u plus our constant, and then we back substitute, so negative 1/3 tangent of the u is 1 minus e to the 3x, and then plus our constant. Okay, so the last page of review. Here we have a situation where there's, in letter O, where there's some e's involved. And so an option might be e to the u, but a little bit more complicated than that. One thing you might consider doing no matter what is rewriting it as e to the 3x times the quantity 1 minus e to the 3x as a quantity to the 1/3. So get rid of the radical. And so it's not a fraction, but it is a power. That is, we have a function of x here being raised to a power. So we're actually going to consider trying to fit the form for the integral of u to the n by choosing u to be that quantity 1 minus e to the 3x that's being raised to the power. And so we're trying to fit, in particular here, u to the 1/3. So the du is calculated. Just be careful again, the negative tags along. Derivative of e to the 3x, e to the 3x times 3. Differential dx as well. Modify, we get negative 1/3 du is equal to e to the 3x times the differential dx. Looking back at the integral, remember we're trying to fit the form of u to the n here, in particular u to the 1/3, the leftovers, e to the 3x, differential dx, compare them to the du, and we see that they match, just modified by the negative 1/3. So replace those by negative 1/3 du, and we're ready for a change of variables because every factor is accounted for. And so therefore we'll bring the negative 1/3 out in front, and our basic formula now is for the integral of u to the 1/3 with respect to u. And so integrating, the negative 1/3 tags along. U to the 1/3 integrates to be u to the power of 1 greater, which is 4/3, divided by that new exponent plus our constant. And then I'll just finish this off to the side. Going to invert and multiply the 4/3, so negative 1/3 times 3/4. Cancel the 3's, we get negative 1/4. Let's put back our u. It was 1 minus e to the 3x. now to the positive 4/3. And don't forget the constant of integration. Okay, so letter L is a special case. This is a situation where you do see a fraction, so you might say du over u, but that's going to be a problem because if you pick u to be the denominator, the derivative of e to the 4x is e to the 4x times 4. We've got an e to the 4x in the numerator, but we've got these extra terms. So it's a fraction where the denominator is not a power, and it does not fit the basic form of du over u. So therefore, we need an algebraic modification. And you should recall seeing this where the denominator is a monomial term or a single term. In algebraically modifying, what we're going to do is use the rule for combining fractions in reverse. That is, if we have a over b plus a over c plus b over c, we have two fractions with the common denominator, we can keep that denominator and combine the numerators. So that's a plus b over c. So what I'm suggesting then is algebraically modifying by reversing the process and dividing that monomial into each term of the numerator. And that concept can be extended to more than two terms, and that's the plan here. I'm going to divide everything in the numerator by that denominator. So e to the 8x gets divided by e to the 4x, plus e to the 4x gets divided by e to the 4x, and then plus the 1 gets divided by e to the 4x. Actually, that was minus 1. And that's all with respect to x. And notice that I actually needed a set of parentheses there because I separated it into three integrals. Now we're going to simplify, and when we're dividing common bases, we keep the base and we subtract the exponents. So this will be e to the 8x minus 4x is 4x. For this next term, we probably just look at that and think cancellation to get 1, but if you thought of dividing common bases, you'd get e to the 0, which is 1. And then think about this final term, and think about the integrable forms that we have. We don't have 1 over e to the u, we have e to the u. So therefore, what we're going to do is we're going to shift this e to the 4x up to the numerator and negate the exponent. So e to the negative 4x. And now that would fit the integrable form. And the nice thing about this problem is at this point, you really don't require a u substitution because these are fitting that special rule that we've mentioned for the linear power, the linear argument. That is, that the integral of e to the kx with respect to x is 1 over k times e to the kx plus our constant. So the first and third integrals fit that form identically of e to the kx. And just to make the integrations even more clear, let's separate this into three integrals. So the integral of e to the 4x with respect to x, then plus the integral of 1 with respect to x, and then minus the integral of e to the negative 4x with respect to x. And now we'll integrate term by term. Again, with respect to the e to the kx rule, e to the 4x becomes 1/4 e to the 4x. Integrating 1 with respect to x, we get x. And we have the minus, and then integrating e to the negative 4x, we get 1 over negative 4, so I'll just make this positive 1/4 e to the negative 4x, and then plus our constant. Okay, so then here's a couple special situations, a couple special formulas. Letter G has to do with a product of algebraics and Trigs. So we know with our integration strategy that Trigs dominate over the algebraics, so we can consider trying to fit the form of tangent of u. But what we should recognize is the fact that that's one of the special formulas. That is, the integral of tangent of u, recall, turns out to be minus the natural log of the absolute value of cosine of u. And I will provide you with that formula on the exam. Everything else is common knowledge. You have to know all the other formulas, but for this particular formula, what I call the other four, recall, integrals of tangents, cotangents, secants, or cosecants, I will provide you with those formulas. So in any event, we're trying to fit the form for tangent of u by choosing our u to be 1 minus x to the fifth. The du is minus 5x to the fourth. Tag along the differential dx as well. Modified by the negative 5, we get negative 1/5 du is x to the fourth dx. And looking back at the integral, we already established we're going to try to fit the form for tangent of u. The leftovers, x to the fourth differential dx, compare them to our du, and we see they match, just modified by that negative 1/5. So we've accounted for all the factors of the integrand. We'll make the change of variables, bring out the negative 1/5, and now we have the basic integral for the integral of tangent of u with respect to u. So at the very least, make sure you know to reference your formulas. Again, I won't force you to memorize this one, but know it's one of what I call the other four. Tangent integrates to be minus natural log absolute value cosine of u plus or constant. And then we'll manipulate the coefficients. We get positive 1/5 natural log absolute value cosine of the u was 1 minus x to the fifth. Close up the absolute values, and then plus or constant. So in letter F, we again see a product of algebraics and Trigs, and we know the Trigs dominate, so we're going to try to fit the form for cosecant of u. And when we get to the point where we integrate, we have to remember this is one of the other four as well. That is, the integral of cosecant of u turns out to be minus natural log absolute value cosecant u plus cotangent u, and then plus or constant. So we'll have to reference that formula at the end, but to begin with, our u substitution, and we're choosing u to be 1 over x squared. So here, as opposed to where u was a polynomial, like the last example, where the differentiation is easy, we'll just have to exercise a little more caution, and first use the negative exponent rule to bring x squared up to the numerator as x to the negative 2. Now the differential du would be negative 2x power 1 less negative 3. Differential dx as well. Then we modify by the negative 2. So we get negative 1/2 du is, and at the same time, let's get rid of the negative exponent on x to the negative 3. Write it as 1 over x cubed. And the differential dx. Then we go back to the integral. We already established we're shooting for cosecant of u. We need the du satisfied, the leftovers, 1 over x cubed, differential dx. Compare them to our du here, and they match, just modified by the negative 1/2. So all factors are accounted for. We're ready for the change of variables. bring out the negative 1/2. And upon the change of variables, we have the basic formula for cosecant of u with respect to u. And cosecant integrates to b, reference the formulas. We'll look back at what the notes that I just provided. And cosecant integrates to be minus natural log absolute value cosecant u plus cotangent u, close up the absolute values, plus or constant, and finally back substitute, so it looks like double negatives make positive, 1/2 natural log absolute value cosecant of u is 1 over x squared plus cotangent of the same u, 1 over x squared, close up the absolute values, and again, don't forget the constant. Okay, so the final two problems, definite integrals, you're going to have 2 of them, and they will be very similar to these examples. In the first example, situation where we see a fraction, so we ask, is the denominator a power? And it is not, it is just a function of x, so we're going to try to fit the form for du over u by choosing u to be the denominator, x squared minus 8. The du is calculated, that's 2x dx, and we modify routinely to get that 1/2 du is x dx. And then we look back at the integral, and we recall we're trying to fit the form for du over u. We've chosen our u to be the denominator, and the x dx that remains, compare it to our du, and we see they match, just modified by the 1/2. So we have all the variables accounted for. We're ready for a change of variables. Bring out the 1/2 integral. We get du over u. But here's that subtle point where we really should not write down 3 to 5, because 3 to 5 is the limits of integration in terms of x. So remember, the technique I use is to use dummy letters, placeholders, column A to B. Then we'll integrate, so 1/2 natural log absolute value of u evaluated from A to B. And then we'll back substitute, so 1/2 natural log absolute value u was x squared minus 8. And now that's evaluated, now we can say 3 to 5. And so upper limit goes in, 1/2 natural log absolute value 5 squared minus 8, minus lower limit goes in, so minus 1/2 natural log absolute value 3 squared minus 8, and finishing this off, we get 1/2 natural log 5 squared is 25, minus 8 is 17, the absolute value is 17, and then minus 1/2 natural log 3 squared is 9, minus 1 is 8, minus 8 is 1, absolute value is 1. And then I would take off a point here if you left that, because you have to know that the natural log of 1 is 0. Natural log of 17 you just want to leave because that's an irrational number if you type it in. So 1/2 natural log of 17. Okay, and then for the final question of the review, it will be this simple with respect to the fact that it's going to fit the form for the integral of e to the x. And recall the formula for e to the kx was 1 over k times e to the kx plus our constant. So immediately, now there's a reason why I'm making this integration so easy. One thing is it's an important formula, but then you'll see what else in a moment. First off, the integration of e to the 4x, 1 over 4 e to the 4x, See, and now we could say we're going from 0 to the natural log of 3 because those are the limits of integration in terms of x, and we're still in terms of x. Now, by the fundamental theorem of calculus, upper limit goes in, so 1/4 e to the 4 times the natural log of 3, minus lower limit goes in, 1/4 e to the 4 times 0. But now we see, and this is the other reason why I made the integration simpler, because I want you to recognize the simplifications here. In the first term we see the base of e with a power that contains a log. And when that's the situation, you want to think of our inverse properties. And the inverse properties involving e and ln are e to the natural log of x is equal to x, and the natural log of e to the x is equal to x. So it looks like it's going to be the first one, e to the natural log of x equals x. But notice how in the inverse property, the power on the base of e, that is the logarithm, has to identically have a coefficient of 1. In our case, we have a coefficient of 4. So what we'll do is just simply use the power property for logarithms in reverse, this is the algebraic power property, and rewrite this as 1/4 e to the natural log of 3 to the 4th power, and then minus 1/4, this would be e to the 0, and that would give us e to the natural log of 3 to the 4th is 81, minus 1/4 e to the 0 is 1, and then by the inverse property, e to the natural log of 81 is 81, so we get 81 over 4 minus 1/4, or 80 over 4, which simplifies nicely to give us 20. Alright, so that's the end of the review, and wish you all the best of luck on the exam, and we'll look forward to seeing you in class.